Okay, so what we are going to do today, though, you had homework to turn in, homework two, or well, the grader will look at that. I'll look at some of them too. But what we're going to talk about is a little bit on I have got my thermistor hooked up. We actually did this last time where we had the thermistor, thermistor here, and it is, mine is not sealed. I still never went back and sealed it. So if you have not sealed yours up to where it can be inserted into liquid water, then you do need to seal this end up, because the way you're going to calibrate yours is with water. So measuring the temperature of water. Has anybody tried to do that yet? Are the thermometers over in the room, or no? No thermometers over there? All right, so I'll have to have some thermometers over there, otherwise you don't have a reference to calibrate. You can put the thermistor in the water and measure stuff, but you don't know what the temperature is. So I'll have to get those over there for you to actually calibrate it. All right, let's look at, we looked at those two things. Let's look at this PowerPoint called Dynamic Measurements. So we'll go through it first, and then there's some examples here that we can look at. Let's see. I guess we can actually, there we go. All right. So these are, we're taking measurements, dynamic measurements. We're taking measurements where things are changing over time. So, here you've got, this is Dr. Hall. he's measuring his temperature, and what you want to happen is, like, you get this instant read of the temperature. The thermometer was at one temperature, and it instantly reads the new temperature. Now, they have actually some really fast, not this style, but some really fast scanner type thermometers that are close to this, but there's still some amount of delay between when you try to measure the thing and when you actually get the measurement. And so that's kind of what this graph over here with the red is looking like, where you're sitting at one temperature, and then over here you've reached some equilibrium temperature, but there's this transient stuff happening between those 2 points. And that's just going to be, anytime you're taking a measurement, there's going to be some amount of time to get from whatever this measurement state was before you tried to measure it to when you actually try to measure it. And so depending on the type of thing you're doing, that can be really fast. Like, you can sample things really, really quickly. But if it's something like in this scenario where something has to change temperature, or it has to change some kind of state, you have to get your sensor to become in equilibrium with whatever you're measuring, then there's going to be a response to that. That's going to take some amount of time, and you need to know how long that time is, so that you don't take your measurement somewhere, in this part of the curve, and you don't get an accurate measurement. So you have to wait for a certain amount of time. Now, I suppose you could have some intelligence in the sensor, where if it notices that the temperature that it's reading is changing, and then it reaches some steady state, maybe you could algorithmically go figure out when to report the temperature. But there's another way to do that. Because sometimes the thing you're measuring changes with time. So, if you don't ever actually get to a steady state, so maybe Dr. Hall is getting hotter and hotter and hotter, or colder and colder and colder, or whatever, and so it never reaches a steady state, you need to know some inherent properties of your measurement system to be able to know when you're taking a valid measurement. So in this one, we're talking about heat transfer. So here you've got a heat transfer equation. Maybe you have taken heat transfer, maybe you're about to take heat transfer, but this equation, you've seen this or a very similar equation way back in 121 when you tried to heat up the water in the little fish tank. And you saw some of these terms, and some of them are obvious, like you got big T for temperature, little t for time. You've got M for mass of what it is you're trying to heat. In this case, the little bulb on the end of the thermometer. You've got C here, which is, well, what kind of material is this bulb made of? Because that would affect how fast and slow it can conduct heat. How big is this thing? So there's an area in here. And so you've got the heat transfer coefficient. That's the material one, the heat capacity of this bulb. And so you've got these terms, and you've got the temperature differential between what's being measured, in this case T mouth, and what your initial temperature of the thing you're doing the measurement, so the temperature of the little bulb down here on the thermometer. So we can rearrange this equation here and get a little bit simpler version. And then these four, mass of the bulb, that doesn't change. The heat capacity of the bulb doesn't change. The heat transfer coefficient of the bulb, technically it might change a little bit when it gets moist or whatever, but it doesn't really change inherently the material that's being used to measure the temperature. So H doesn't really change. The area of it, again, maybe it expands and contracts a little bit, but in the big scheme of things, that area doesn't really change. And so these are more or less a constant, with the potential that some of them change tiny amounts, but they're tiny enough that it doesn't actually affect anything that we're trying to measure on the scale we're trying to measure them. So these four get lumped into what's called a time constant. And so that time constant kind of controls this part of the response of your system. So it controls how long does it take for your measurement system to get from its initial state to its equilibrium with the thing it's measuring state. And so that time constant is, in this case, built of these four items. Now you could go and like measure these things and calculate the time constant that way. That's not normally, or it's not often how it's done. Normally it's part of the calibration of your instrumentation is to figure out this time constant. That's what we're going to do. So this is a first order system. So, higher order systems would have basically more wave looking patterns in here. So it would have more lumps on the graph. So these first order systems, they normally have something to do with energy storage. So in this case, it's heat energy, since we're doing temperature measurements. And here's just a generic, maybe you haven't taken any classes that explain this solution to a first order system yet. You'll get to those if you haven't already taken those. But this is just the generic solution to a first order system. So you've got a bunch of terms in here, some SS's and some naughts. This little tau, you can see that. Zoom in a little bit. That little tau right there, that's the time constant. The lowercase t is just t, and then you got exponential e. Oh, do I have to zoom back out for it to? There we go. All right, so x, the one with no subscript, that's the actual response. So maybe it's like the plot. X naught is the initial value for x. So down here somewhere. XSS is the steady state value. These are x's, but they're not actually like the x-axis. So don't confuse that part. They're just labeled as x's. So a steady state, that's this final, kind of it's leveled off after some amount of time. Then that's the steady state value. Like we said, lowercase t is just time. That is the x-axis on these kind of plots. And then tau is the time constant. It doesn't really show up on the plot by itself, but it is describing the shape of this curved section. Okay, there's labels for x naught and xs. All right, so we have I put on Moodle a file called Thermistor Data.tsv. So that should be in Moodle. Yeah, right there. Thermistor Data, hopefully .tsv is the extension. You might have to name it that when you download it. So let's get that thing. Yeah, it does come up as TSV. So we've got this Thermistor Data.tsv. We need to put that in the folder we're going to, let me get to it. The same folder that we're going to use for our Python code and all that kind of stuff. So I've got mine over here in my 382 folder in class. Mine are just all lumped together. So we'll just lump it in with that and it'll be okay. But I got to find where I put it now. Let's see. All right, there it is. Oh. So let's take thermistor data, put in here. So this is as if, well, we can look at it. It's the same thing from last time where there's something that relates to a time, I suppose, here, and a value that relates to temperature. So this is more or less, now I don't think this is the time format that the simple Arduino that we had last time displays. I think that displays milliseconds, and this looks like maybe it's more seconds. So it's just a converted a little bit differently instead of just straight up milliseconds. So we've got a whole string of that data, and what this is, you can see the temperature. It's not temperature, but the analog read value related to temperature ends up in the 800s, started in the 480s. So there's some change there. So basically what happened is we set up our thermistor just the way we have this one, and we put it in something like warm water and recorded the data over time from 0 to, let's see how long we recorded it. 100 seconds. So we have 100 seconds worth of this temperature data. And it's just built into this file so that you don't have to go build your own file to do what we're going to do in class. So that's just that thermistor data. All right. Now let's go back. It just minimized it in this tiny little thing. All right. So thermistor data. So ADC equation. So ADC is analog to digital conversion. And this is, we kind of wrote it out last time, but this is basically AR is the analog read. That's the 480 number to up to 800, whatever number on our data set. But it can range anywhere from 0 to 1023. And then the 5 volts over 1023 is because 5 volts is our reference voltage that we have set up on the Arduino. You can change that to different references, but by default, if you don't do anything, it defaults to 5 volts. The 1023 is because we're using a 10-bit A to D converter on the Arduino, and that's just built into the Arduino. You can't really change that without adding hardware. So 1023 is 2 to the 10th power. So that would be the 10-bit part of the converter. If you had a 12-bit converter, then this 1023 gets to be a larger number, 2 to the 12th power, so that you have more little divisions in your conversion, and basically you can measure smaller things, smaller increments. And then V2 is the actual voltage. So V2 is the voltage that relates to these numbers like 480 and 800 or whatever the analog read value. It's just the actual voltage that relates to that. And then this is the voltage divider equation. So here, let's get something we can draw on it real quick. Let's see, where's drawing this? That was from last time. So we have built basically a voltage divider. So remember, we have 5 volts. This 5 volts here is not the reference voltage. This is the 5 volts powering our little thermistor setup. And it goes into a thermistor. So this thing changes its value with temperature. And it's nominally 10,000 ohms. And then we've got a node here. And we've got a static, a resistor that does not change. And it is just 10,000 ohms. And we go to ground. So I've got the voltage divider is just 2 resistors in series. That's all it is. And the divider part is basically this 5 volts gets divided between, some of it goes in the first resistor and some of it goes in the second resistor. And the sum of those two is 5 volts. And so the 5 volts gets divided somehow. If they're both equal, if they're both 10,000 ohms, then it gets divided evenly. So we're measuring right here. So we have tapped into this node with, well, I'll put an orange wire on mine, I'll put it red here, with a wire that goes over to pin A1, so analog read 1 on our Arduino. And we're measuring from there to ground, basically. So this potential, that's the voltage that we're actually measuring the voltage in that 10,000 ohm resistor. And we're doing it that way because we're using NTC style thermistors, so that's negative temperature coefficient. So their response is inverse from what you would want, basically. So in other words, temperature goes up, the resistance goes down. So they don't have a positive temperature coefficient. There are some like that. Typically, the positive temperature coefficient thermistors are used more like a shutdown switch or a fuse or something, where as their temperature increases, their resistance increases. So you can imagine this little thermistor is in some electronics somewhere and it's overheating, and as the electronics are overheating, the thermistor is getting hotter, and the thermistor gets hotter, its resistance gets higher. And so if this guy's resistance gets higher, then it kind of just shuts down everything else. You know, it's more resistive. So it's kind of helping to prevent against some kind of thermal runaway type thing. So we're measuring the other one. All that to say, we have an NTC style, and we're measuring the voltage in the 10K guy. And that's what this equation here, VS, V2, those are the two different voltages, RT and R2, and then there's a -1 in there, the way you rearrange the equation. So this equation will let us, since we're measuring the voltage in the 10K static resistor, then we actually want to know the temperature, or not the temperature, well, we want to know the temperature that the thermistor is experiencing, but to do that, we need to know the resistance of the thermistor. So this RT is the resistance of the thermistor. So this little equation helps us get from the voltage we measured over to the resistance of the thermistor. And then this last equation down here, this is the manufacturer's equation for how to calculate the temperature, assuming you know the resistance of the thermistor. So that came from the manufacturer somewhere. And the manufacturer gives us a specific value for this B depending on what thermistor we bought. All right, so those equations, I believe, let's open up, I think it's going to be in maybe example 1. Let's open up example 1 and see if they're built into there. Yeah, they are. See, they're right here. Well, part of them are right here. There's the V2, there's the RT. This one we haven't talked about yet. So this example 1 is Python code that can go in, well, look at it. It's going to go in and read, oh, you know what? It's going to read this thermistor data in a specific path. So I did not put my thermistor data file in a data folder. So I might have to go change this or move my thermistor data for this code to actually work, because it's looking for it in a folder called data/thermistor data.tsv. So all of our data is in this file. This Python code reads it. In a minute, we'll go through and walk through this, but let's carry on right now with what we're actually going to do with it. So here's the data if we plotted it. I think this is the thermistor data. And you can kind of see it. It looks really close to what we showed, like the perfect example with the thermometer. It's got a little bit of, here's a little overshoot right here. See, here's our steady state value over here, and it kind of has a little hump before that. So it's got a little overshoot. There might be a little bit of creep type stuff here. You know, it's kind of decreasing slowly. You know, where's that? What's causing that? I don't know. But there's more or less the steady state region here where it's not really changing. The temperature measurement is not really changing that much. And over here, you've got a few points of an initial state, you know, this little flat line down here. Our code goes in and, well, this part of the code is just kind of separating out the data into time and analog read values, and it plots it. So all of that's plotting it. And then it goes in and it tries to find those areas. So it tries to find this little initial area and figure out what that temperature is. It turns out to be 295.2 Kelvin. Then it tries to go and find this area. Turns out that that's about 341.7 Kelvin. Now, I think the code that we have that I was just looking at actually kind of hard codes this in. Basically, it it knows at the beginning is the initial value, and it knows to after about 50 seconds, then you can start averaging those values to figure out the steady state. It could be more sophisticated where it goes and looks at the change in this value and says where steady state occurs, but I think we kind of hard coded it in. We'll look at that when we look through the code. All right, so here's that equation that we said was the solution for a first order equation and our response equation. So there's S, so the steady state value, and again, these X's are not X values, they're actually on our chart, they're the Y axis, so they're the temperature values. So don't get worried with thinking you got to put an X axis number into these X labeled things. So what you do is basically you know all of these things except for tau. So you go and plug in what you know. So we take our generic equation right here, and we set a special point where the time equals tau. So tau is basically going to be a special point. Well, let's just go up a slide. Tau is going to be a special point on this curved portion of the graph. Remember, it's called the time constant. So it's about a point that's 63%. Once your response has reached 63%-ish of your steady state value, that's where tau is how long does that take. So it's at this point where t is tau, so everywhere there was a t, so there's a t here, and there's a t in this little power over here, negative t. So we put both of those t's as tau. So there's a tau in this first part. In this one, when I put e to the negative t, I put a tau in there, I get e to the negative tau over tau, so that's why it became e to the negative 1. And I can just evaluate e to the negative 1. And the steady state value, I read that off the chart. Remember, we decided that our steady state value was 341.7 Kelvin, and our initial value was 295.2. So there are those numbers, 341.7 and 295.2 Kelvin. And then this steady state is just 341.7 Kelvin. So all this is rearranging this equation, and t equals this variable tau. And what I end up with is the value where x of tau, and now not x of tau, but the temperature at tau is 324.6 Kelvin. So 324, this is really small, but let's see, 320, 330, so there's 325. So we're talking about like right there. So I'm looking at that data point, and I go and read that value, which, I don't know, there's 10, there's like 5, maybe it's a little over 5, I don't know. Let's see what it actually says it is. 3 point, so it's a little less than 5. I didn't do my drawing very well. This picture has it drawn on there already. Well, no, it didn't. Oh, right. So we actually plug in that value. So I read it off the data. See this red line here? They have actually generated this equation. Well, I didn't want to move that. Well, that's okay. We'll just zoom out. Where we've plugged in all the values and solved for what temperature, the temperature of, what was it? 324.6. So that temperature gives you a tau of 3.92 seconds. So it takes 3.92 seconds to reach basically 63% of our steady state value. Now notice it's not perfect. Like that generates a curve, this red line, that is not exactly like the blue data that we collected, but it's similar. And so what we're not, you can see where the blue data overshoots a little bit and then comes back down. So there's something more than just a direct first order response that we expected, because we get a little bit different curve than the first order curve that we generated, but it's okay. It's close, and so you have to decide, is it close enough? Let's see. This is a different way to solve for the time constant, where you use the Heaviside function, which is basically a step function. It's just a different way to do it. So here are two sets of data. So we've got one set of data from system one set of data from system two. They have different responses. One of them, is getting, I don't know if it's temperature or, well, it's really small numbers, like it goes up to 1.75. So it's not temperature probably, but whatever it is, one of them goes up from a lower number, and then one of them goes down from a higher number. And the question is, which has a higher time constant? And so what you can do is you can estimate, just looking at we're going to calculate it on the next slide, but we can estimate, here is basically the initial starting, I don't know, 0.25, and then it goes up to 1.75. So it takes, I don't know, maybe something like this long to get to 63%. So that's like 0.5 seconds, or no, 5 seconds. This one, the initial is here and the steady state is way over here. So 63% of that's somewhere over here. And it takes, I don't know, a little over 5. I'm just guessing. I'm not measuring anything. This one could easily, I could be convinced that it's over here. And, it's like 3 seconds or whatever. So just looking at the graph, you can tell that system 2 has a longer response time. It takes longer to get from your initial value to your steady state value. So it has a larger time constant. That's not a great way to go calculate the time constant, but you can just look at them and determine that system 2 has a longer time constant. To calculate them would look something like that. Now this has got, I don't know why, but they're both on the same slide. And you can calculate them. This is the two different methods for calculating them also. So over here is basically the one that we just did with the temperature data. So we found our, and this is from the plot. So we don't have the actual data. We just have the plot to read. Maybe we should get some of these out of the way. Oh, can I not? There we go. All right, get that out of the way so it's not confusing us. All right. So the initial value for system 1, I don't know, it looks like it can't tell if it's at 0.25. It looks like it starts a little above 0.25. Maybe we would know better if we had the data. We put in the initial value of 0.3 because it looks like it starts a little bit above 0.25. The steady state value 1.8. So steady state, it goes to right about there. So yeah, okay, 1.8. And notice these are approximately that. So we're not going to go read the actual data. We're reading this off the chart. And this is very much something that you might end up having to do on an exam. Get a chart with some numbers and calculate, based on reading the chart, the time constant for that system. So we got our initial and our steady state values. Here's that first order equation again. We're going to put in t equals tau. So x of t becomes x of tau. We're going to put in our values of 1.8. Again, this isn't using units, but the units would end up, depending on what we solve for, we don't even know the units really, do we? We just know it's system 1 response. So these things do have units. Time constant is in time, so it's going to be seconds. So steady state values go in as 1.8. The initial value goes in at 0.3. E to the -1 because we put in tau right there, and we end up with negative tau over tau, so that is -1. E to the -1 is that number, so you can plug that into your calculator, and that lets you solve for a value of x of tau is 1.25, so 1.25 is right here. That's really close to 2.5, and that's what they estimate. Tau is about 2.5 seconds. And then you can go in now, and this is basically this equation with the t back in it instead of tau. So except now you know what tau is, so you can put in tau is 2.5 and return all of the t variables to just t. And now you have an equation that you could graph this equation, the one in the box at the bottom, and it would, oh, I keep doing the wrong thing. It would generate a curve that looks more or less like this one. But it would be, instead of all the data points, it would be a smooth curve that represents that same response. So that system had a time constant of about 2.5 seconds, and that's all just reading it off the graph and solving that one equation. So it is an approximation, you know, if we had the data or whatever. But even then, if you have the actual data points, that doesn't really help, because you're trying to take these data points, and it's kind of like curve fitting. It's like a linear regression or whatever. It's kind of like curve fitting. So you can't, depending on what point you picked, you would end up with generating a different curve. So it is really, looking at it, you could probably write some algorithms that went in and averaged everything out and got you a pretty good value. But as long as you're careful reading from your chart, then you'll get a good enough for what we're going to do answer of your time constant. All right, this other system too, we could do the same thing, but we're going to use, where to put it? We're going to use this approach where we're using this derivative in here. So we'll use the slope. So basically we're going to start with what's the slope at this beginning point of this line, and we're going to calculate the time constant with that approach. So x naught for this one, the original point, a little less than 1.5. They called it 1.4 in our example here. So, and the steady state is more or less down here at 0.25. So that's where these numbers, 1.4 and 0.25, those are our y values, or the temperature value, whatever that we're measuring. Those are the measurement values at the initial point, and once it's gotten to steady state. And then this is the equation, we just have it from over here. Keep zooming in. It's just this rearranged. So we've got basically the slope at 0, so time 0, is equal to x2 minus x1. So basically you're just calculating the slope. Now this is where you could get different numbers pretty easily, because what has happened here is we're on our graph and we want to know the slope at time 0. So you have to go in and you have to kind of estimate the slope. So and pick what this right here, what this is doing is just basically calculating the slope at time 0 based on the graph. So you've got maybe a point here and a point here. You know this point because it's the 0 point, so that's a good one. And then this other one, you're kind of trying to estimate the slope, and it would be really easy to draw a different line in here, to get the slope from. So that one, there's a pretty wide margin if you're just using the graph. Now we do have a Python code that's called maybe linear regression, I think, on Moodle, that will help you get this slope if you are using the data versus reading it off the graph. Anyway, they picked, I think they actually picked the point that I drew through, because their x and so they're using x and t. So t is actually the x-axis, and x2, x1, those are actually y values on the chart anyway. So they did pick 0 and 1.4. So that's this point. X of 0, y of 1.4, that's that point. And then over here, they picked 2.5 and 0.5. So on our chart, that is the one I picked. So 2.5 and 0.5. So using those 2 points, or whichever two make the most sense for your slope, you calculate this initial slope, the x naught, x dot naught, so the slope at 0. So once you know the slope at 0, which is negative 0.36 for us if you use those 2 points, then you can solve this equation because you've got tau, you've got the steady state value, which we read off the graph as 0.25, the initial value that we read off the graph as 1.4, and then that slope that you calculated, and you plug all those numbers in. There's the slope going in right there, and steady state and initial value, and you get a time constant, 3.19. And then here, this is going back to the same thing we did before, where we just take this equation, same equation there actually, and plug in our steady state value, our initial value, and the time constant that we just calculated. So the two time constants, system 1 had a time constant of about 2.5 seconds. System 2 had one about 3.19. Now, can you actually get that down to 3.19? Probably not. It probably should be like 3.2. But just because we're reading it off a graph. But it does, there's a big enough gap between 2.5 and 3.2 to pretty definitively say, even reading it off the graph, that system 2 has a larger time constant. It's just what they boxed in right here. So those are two ways. One where you're using the steady state and initial value to calculate the time constant, and one where you're using the initial slope, steady state, and initial value to calculate the time constant. So both of them, and they're both for first order. So these, when you plug them into this equation, that assumes that you're using a first order, you want it to look like a first order response. So if